Okay, so you all got your first work set back, and the grades look pretty good. So apart from just a couple of you, most of you got anywhere from 19 to 25 out of 25. So that was well done. I hope you also did a good job on the second one, and then the third one is due next week. And then there won't be one for 2.5 weeks, because the week after next, you're going to have some free time so that you can prepare for your midterm, which is in 2 weeks from Thursday. Okay, so any questions so far about the material? Just checking to see that on. So what we're going to do today is we're going to move on from our focus primarily on discrete models, where we were looking at models of the kind x at t plus 1 is some function of x at time t, to continuous models, and we'll start off either using n or x is some function of n. Now, we've seen the discrete models in the context of exponential growth, and we talked about it early on, just so that we could contrast it with the discrete models. We talked about the continuous models. But from now on, for the next couple of lectures, we're going to focus on this class of models and develop concepts from harvesting theory that go back to the 1950s and 60s, and introduce some of the classical notions that underlie what's called the field of bioeconomic theory. Now, if you remember, one of the models we had was a model where we said we've got some constant r, I'm going to write capital R here, times n. And that would be exponential growth if r was greater than 1, and exponential decay if r was less than 1. But now we're going to talk about the case where r itself is some function of n. And in particular, we're going to have the simple case where r as a function of n is equal to little r 1 minus n upon k. So if we were to draw that function, what would it look like? If we were to draw r upon n versus n, so this would be the case of constant r, which would lead to the exponential model. Okay, but now r is no longer a constant. It's a function of n. So what does it look like in this case? What is this? What kind of function of n is this? Huh? Well, this will be the logistic if this is what? How does this depend on n? What power of n is in there? Linear. It's a linear model. So it starts out, let's say, at the value r. So this is the case, r of n equals little r. Then we get exponential growth. So if this is little r, then it's just a constant. But now, it intersects at k. And so we call k the carrying capacity. And if we do that, we write down the model, dn dt is equal to r times n into 1 minus n upon k. So if the per capita growth rate is linear, then the right-hand side is, what do we call this as a function of n? What do we call this? What power is n? What's the highest power of n? N squared. So what do you call that? You can say it. Begins with a q. Quadratic. Okay. Quadratic. Okay. So not only is it a quadratic model, but it's also the quadratic model. If we write this as a function of n, and we write here f of n versus n, then remember, this is the per capita rate of growth. This is the total rate of growth. So it's the per capita times n to get the total. Then this becomes quadratic. And it goes through 0, and it also goes through k, and it has a maximum. Now, would you know how to integrate that function, how to solve it? So we've got the function dn dt equals rn 1 minus n upon k. Now, just to recap, when dn dt was equal to r times n, r a constant, so this was the exponential model, and this is called the logistic model. Do you remember what the solution to this is if we specify n at time 0 is equal to some fixed value n0, some given value? What would the answer to this be? Remember we integrated this. What was the solution? How many had Red Bull before they came to this class? Maybe you all need a little caffeine before you come to class. I know this is a horrible time of the day because kind of the lull when you have lunch. What happens when I integrate this? What's the solution? It's the exponential equation. N at time t equals n0 e to the rt. Remember that. So I went over this in one of the earlier lectures, and I said, you've got to remember this. Now, in the same way, you can integrate this, and when you do, if you go to the textbook, you'll see that, firstly, there's a qualitative, example 6 is the qualitative behavior of this equation. We'll talk about that in a minute. But if you have a look at example 7 of section 6.1, we've written down a specific equation there with little r equal to 0.53 and k equals 660. And if you remember Carlson's yeast data, it turns out that this fits nicely through the yeast data. There it is. So we talked about Carlson's yeast data earlier on. And this model fits nicely through it. And how do you integrate it? Well, you integrate it using the method of partial fractions. So this expression, 1 over n, 1 minus n over 60, can be written as 1 over n plus 660 minus n. So you can split this fraction up. So you start out with the equation at the top over there. Do you want to just switch the lights off? That's that one. Yeah, thanks. Okay, great. So you start out with this equation at the top. And what you do is you take this equation, dn dt, and you divide both sides by n times 1 minus n over 660, and then you integrate that. So you get, it looks like, if you remember the exponential equation, that's what we did, except now you've got two terms when you use the method of partial fraction. And so the first term is log the modulus of n, and the second term is log the modulus of 660 minus n. And you integrate this, and then you find out that the solution can be written in this form. So it looks like an exponential, except it's got this denominator that also involves an exponential. But you can multiply the top and bottom by e to the minus 0.53t, which would cancel with this term, but would make this term e to the minus 0.53t. So when you get the general solution to the exponential, you can show that the general solution has a form that looks like this. Where is it? It's here somewhere. There it is. So this is written in terms of r, k, and this is for x rather than for n. But this is the logistic equation. So the logistic equation, if you integrate it for general r and general k, depends on the initial value, and on k, and on r, and it's a function of time. Okay, I'm not going to ask you to integrate that in your exam or anything, but I think it's just nice for you to see it. Now, how does the logistic equation behave? So can we switch the lights on again? Thanks. Okay, so the easiest way to see what's going on is to have a look at this function f. And so when I find a solution, what do I mean by that? It means that I'm plotting n over here as a function of time. So this graph here plots the right-hand side as a function of n. The solution plots n as a function of time. Now, if we look at the right-hand side, when is the right-hand side changing its most rapidly on the interval 0k? Well, firstly, if we have a look at this, we realize that between 0 and k, the right-hand side has what sign? What is the sign of the right-hand side? Is it positive or negative? When n lies between 0 and k, is this positive or negative? Positive. And you can see you've drawn it positive. It's 0 over here, and positive. So where does it have a maximum? Where's its maximum rate of change? Where this is the highest. And this is a quadratic. So those of you who remember, this is the middle, and it's k upon 2. So it's halfway between 0 and k, because being a quadratic, it's symmetric. So it has its maximum over here. So that means the maximum rate of change of the population is going to be at n equal to k upon 2. So let's draw over here. This is n equal to k. This is n equal to 0. And this is n equal to k upon 2. Okay, so now what happens if I... Where are my markers? A mystery. Anybody see my markers? No, those aren't mine. Those are the ones that don't work. This is crazy. Okay, well, we'll try the ones that don't work. I guess mine will turn up somewhere. Anybody who spots them can get an extra X number of points. Huh? They're 4 different colors. Well, I haven't said what X is, so there's no incentive yet. Okay, so let's say we start out at N0, which is rather small, over here. Yeah. No. They're not. Probably. Okay, great. Okay, you get X. We'll have to see what X is later. Okay, so now we've got decent markers. Okay, so we start out at N0. Let's say it's small. The population, when n is small, n upon k is small, this is close to 1, the population is growing like just this term, which is an exponential growth. And then it keeps increasing, and it's at its maximum growth over here. Now, as n approaches k, this term approaches 1 minus 1. It approaches something very small. So you're multiplying this by a small number, and this number, as n gets closer and closer to k, gets closer and closer to 0. At n equal to k, at n equal to 0 or k, we have dn dt is equal to 0. So if we start out at 0, we stay at 0. If we start out at k, we stay at k. Those are called the equilibria. But what happens is the population grows less and less slowly, or more and more slowly as it approaches k. So it starts out growing exponentially. If this is the maximum growth rate at this point, what can you say about the tangent to the curve at this point? The tangent to this curve at this point is the steepest. So this curve gets steeper and steeper, and then it gets shallower and shallower, because it's got the tangent is given by, well, the growth rate is maximized over here, so the tangent must be a maximum. This is where the population is growing fastest. You can also show that if you start out, let's say over here, above, if n0 starts above k, what is the right-hand side? Well, it turns out that you're now in this region, and this curve is below the line, so it's negative. So if you start out above k, then the population declines. Can the trajectory, can you get a solution that crosses this point? Could you get a solution that crosses? What do you think? What happens when you're at this point? Right, so what happens to the right-hand side of the equation, dn dt? When n is equal to k, dn dt is 0. So if you here, the rate of change is 0. So you can't cross it, because to cross it, you've got to be decreasing to go through it, okay? So that's the qualitative behavior of that system. Okay, so you can read this stuff yourself. And you can also look at the logistic growth curve for the Carlson's yeast data. But now what we're going to do is we're going to talk about harvesting. So when it comes to harvesting, we modify this equation by putting in a harvesting term. So we can put in a harvesting term by adding a function h. Okay. Now if h is a constant, then this says we're constantly removing individuals from the population. So imagine a population is growing out there, and in this case, there's we looked at the logistic growth for Carlson's data. But in harvesting, an example here is harvesting queen conchs. Now conchs are those big snails that come in these big shells, and they're supposedly good to eat. Has anybody ever eaten one? It was good. How was it prepared? What's the butter? Garlic. Okay. But you have to go to the Bahamas. Yeah, so I guess in Florida they can. So when you're harvesting, you can say, suppose the population out there grows logistically and it's at its carrying capacity. What happens if I come along and I remove 21,000 individuals per year? So in this case, my rates are in years. This is the growth rate of the population per year. The carrying capacity doesn't have units of time. It just has units of n. And so if, for example, r is equal to 10, that means the population grows very rapidly, then you can ask, what happens if the carrying capacity is 10,000 and I'm removing 21,000 a year? Well, what you do is you can say, can I sustainably harvest the population if this is my model? So I've got a queen conch population. I somehow know that this is a model, 10 times n, 1 minus n upon 10,000. So it's in a particular area. It has a carrying capacity of 10,000. Now, when I harvest 21,000 a year, I'm not doing it all at one time. Every day, I'm harvesting 21,000 divided by 365 individuals. So there's kind of this constant removal. Does this population have an equilibrium? So we do what is called a qualitative analysis. And to do this qualitative analysis, we say, is there an equilibrium solution to this model? So let me write it down. dn dt is equal to 10n, 1 minus n upon k, minus, and now h is 21,000. Does this model, the first thing I ask is it possible that I can have an equilibrium solution here? So is it possible to have an equilibrium? How would I answer that question? How would I answer the question? Yeah? How do you answer the question? Well, in this case, an equilibrium means that the dn/dt is not changing. So you're right if it's a discrete equation. If it's a continuous equation, you've got to set it to 0. If it's a discrete equation, you've got to set it equal to its value. So what we have to do is we have to solve the equation for an equilibrium, 10n into 1 minus n upon k, minus 21,000 is equal to 0. And when I solve this equation, as I do here, I find out that there are two solutions. N equal to 3,000 is the one solution, and the other solution is n equals 7,000. Now I ask you what happens if, for example, instead of putting 21,000 there, I put 30,000. So if instead of 21,000, I have 30,000 in there, and I try to solve that, I find out that I can't get a positive solution. In fact, if I set this equal to 25,000, then I get only one solution. So what's actually happening here? So in this particular problem, what is happening is that if I draw the curve, f of n versus n, and this is over here, k, which is 10,000, and I draw this function, then, and this is 5,000. If I put n equal to 5,000, and then I've got 5,000 times 10, which is 50,000, into 1 minus 5,000 times 10,000, which is a half, I get 25,000. So it means that the height of this over here is 25,000. So when I'm at 21,000, when h is equal to 21,000, so this is h equals 21,000, or h equals 30,000. So I'm plotting f of n, and I'm plotting h on this axis. When h is equal to 21,000, it intersects over here at 3,000, and over here at 7,000.